So today we will continue our discussion of NP-Completeness. Today most of the lecture is going to be examples on NP-Completeness reductions. Okay. So before we start giving these examples, let's review the main concepts in the last lecture. The main concept was the definition of NP-completeness. A problem is NP-complete if both of the following conditions are satisfied. Condition number one, the problem belongs to NP. A problem, let's give it a name. L is NP-complete. L belongs to NP. And what does L belong to NP mean? Yeah, exactly. Verifiable in polynomial time. In polynomial time. And the other condition is every problem in NP is reducible to this problem. So every problem L prime in NP okay, so maybe for every problem L prime that belongs to NP, L prime is polynomially reducible to L. Okay, so these are the conditions. Now, is the second condition hard or easy to check in practice? Is it hard or easy to check or to prove that for every problem in NP, that problem is reducible to L? It's hard because you have to prove this for every problem in NP. So now, last time we offered an easier condition, a condition that is equivalent but is easier to check. And what's that? What was that?
L star.
Mm-hmm. So instead of trying to reduce every problem in NP to L, we reduce an NP-complete problem, one known NP-complete problem to L. And why is that valid? Why can we reduce only one NP-complete problem to L instead of reducing every problem in NP to L? Why will that still be valid? Yes?
Because all the NP-complete problems were reduced or are still reducible to each other.
The NP-complete problems are reducible to each other. So if I have a problem L star that is known to be NP-complete, so I know that L prime is polynomially reducible to L star for every L prime in NP. Now, if I can take L star and reduce it to L, then I have proven that every problem in NP is reducible to L, because L star is at the highest level of difficulty in NP. It has been proven. Remember our example last time about the tallness, about finding the tallest people, the tallest group of people. Okay, once you find one of those tallest people, then you can use one of them to compare with. So you don't have to compare with everyone. Okay, so the equivalent condition is equivalent condition for number 2. So this is an and. Both of these conditions must be satisfied. But there is an equivalent condition for number 2, which is for some for some NP-complete problem L star is polynomially reducible to L. So this condition in blue is much easier to verify in practice because you only need to find one problem. And reducing one problem to another is easier than trying to produce an infinite number of problems in the abstract. Abstractly reducing an infinite number of problems to one problem. Okay? Especially if you can find a problem that's very similar to the problem that you are trying to prove. And today we will be looking into some actual examples. Now the last thing to review the theory, if a problem satisfies condition 2 but does not satisfy 1, what do we call it?
NP hard.
We call it NP hard. And the example that we gave last time was, so what was the example for an NP complete and an NP hard problem?
If it's an optimization will
Yeah, so the optimization version of the traveling salesman problem is NP hard because the optimization version does not belong to NP. And why doesn't the optimization version belong to NP?
because you can't check the solution in polynomial.
Yes, because you cannot verify a solution in polynomial. So if someone gives you a proposed solution or someone claims that this is the solution, you can't verify if it's optimal or not in polynomial time. Unlike the decision version of the traveling salesman problem. The decision version of the traveling salesman problem can be verified in polynomial time, because if someone gives you a proposed solution, if someone claims that this is a solution, you can verify in polynomial time that it's correct by checking that it's a valid solution, checking the vertices, checking that the vertices belong to the graph, and checking that they are not repeating any vertices, and checking that, what else? For the traveling.
All the target values below that value.
Well, the sum of weights, the sum of edge weights on the proposed cycle is less than or equal to the target cost. So there is a target cost that we are trying to meet. So the sum of weights on the proposed solution of the edges in the proposed solution has to be less than or equal to the target. Okay? So that's, you know, NP complete versus NP hard. Okay? So now let's use this to prove some problems to be NP complete. First, let's introduce the following problem, the Hamiltonian cycle problem. Or Ham cycle. So this problem, you are given a graph, and the problem is to determine whether there is a simple cycle in the graph that can visit all vertices. Okay. Which means, is there a traveling salesman tour? But now you are given a graph. In the Ham problem, you are given a graph and you are asked to determine if there is a simple cycle that goes through all vertices. While in the traveling salesman problem, the objective is different. In the traveling salesman problem, you are guaranteed to find a cycle that goes through all vertices. You are guaranteed to find a simple cycle that goes through all vertices. Why is that?
It is a complete graph.
Exactly, because it's a complete graph. So in the traveling salesman problem, because it's a complete graph, the input is guaranteed to be complete. You are guaranteed to find anything that you want, any kind of path, any kind of cycle that you want. So you are guaranteed to find a simple cycle that goes through all vertices. So there is no question about this. But now in the traveling salesman problem, we're trying to find a simple cycle that goes through all vertices and has minimum cost, with minimum cost in the optimization version, or with a cost that meets a certain target in the decision version of the traveling salesman problem. Okay? Now, the Hamiltonian cycle problem, given a graph, determine. So when I use the word determine, will this be then a decision problem or an optimization problem? Decision. So determine if yes or no, then it's a decision problem. Determine if the graph has a simple cycle that goes through all vertices. Okay, well, so let's look at some examples to understand the problem. So let's take an example of a graph that is Hamiltonian, for which the answer is yes. That's easy. So this is a graph that is Hamiltonian. A, B, C, D. This is Hamiltonian, and there is an obvious simple cycle that goes through all vertices, which is this. Now, in order to illustrate the concept, we have to give an example of a graph that is not Hamiltonian. So this graph is not Hamiltonian. A, B, C, D, E. Okay. Now, can you find a simple cycle that goes through all vertices? You will not be able to. So if you try this, you start from A, then you go to B, then you go to C. Okay, so far we have visited A, B, C. Now we have a problem. Now we need to visit both E and D. And we cannot visit a vertex more than once. So if we go to E, we either go back, which is not allowed. So in order to get to D, we either go back or we go to A again. So in either case, we'll have to go through the same vertex more than once. And if we choose to go this way, we will just skip. If we go this way, we'll skip E. So there is no simple cycle that can go through all vertices. So this graph is not Hamiltonian. And this is Hamiltonian. Yeah?
Are we assuming that the source is at A?
It doesn't matter. It's a cycle. So you can start from any vertex you want.
Oh, yeah, that's right.
It's a cycle. So you can start. Can you see a cycle that starts from another vertex?
No, because I remembered that you said it had to be a cycle. Because I was originally thinking you could go B, C, D, A, E. But then that's not a cycle because you can't go back to B. Yeah.
Yeah. So it could be a cycle, but not a simple cycle. So you cannot find a simple cycle, right? You can find a non-simple cycle, a cycle that visits the same vertex more than once. But that's not what we want. We want a simple cycle. And so this is not a Hamiltonian. So this is an NP-complete problem. It doesn't have a polynomial time solution. So in this case, what's the brute force solution? What's the brute force solution to this problem? Yeah, so the brute force solution is to try
everyone.
all possible paths. Yeah, all possible paths or all possible permutations. Some of the permutations may give you valid cycles, some of them may not, right? Because not any permutation will give a valid cycle or even a valid path, because you may not have the edges for that. So you may or may not have the edges. But if you try all possible permutations, that's n factorial or v factorial. Okay. So this is a known NP-complete problem. Now, is this a decision or an optimization? This is a decision problem. Now our example is, Now, okay, so this is the example. Given that Hamiltonian cycle is known to be NP-complete, given that Ham cycle is known to be NP-complete, prove that TSP is NP-complete. Now, which form of TSP is NP-complete? Is it the decision or the optimization? The decision, yeah. The decision, TSP decision, is NP-complete. Well, now we have to verify that traveling salesman problem satisfies both conditions. Now, this condition is easy, and we have just talked about it. So condition 1, in order to prove that a problem is NP-complete, you have to prove that both conditions are correct. So condition number 1, which is the polynomial time verifiability of traveling salesman decision, we have just said how to do that. You verify that all the vertices, the valid vertices, no repetition of vertices, and that the sum of edge weights on the proposed solution or proposed cycle, the sum of weights is less than or equal to the given target. Okay? So now this part, so we know it. So I'm not gonna write this down. So I'm gonna leave it for you to write it down. The interesting part is this. Of course, we're gonna use the blue condition, and we will be using Hamiltonian cycle as the problem that is known to be NP-complete to prove the NP-completeness of traveling salesman problem. So we need a reduction. We need a reduction from Ham cycle to TSP or TSP to Ham cycle. Yeah, from Ham cycle, from Ham to TSP. So we need to show that Ham Ham is polynomially reducible to TSP. Again, never get confused with these. So we are trying to show that there are multiple ways of interpreting this. You can easily look at the mnemonic, which is less than or equal. The less than or equal sign being used here is a very good mnemonic. It just means that this is known to be NP-complete. And the problem that I'm trying to prove, I'm going to prove that it's greater than or equal to this problem in terms of the level of difficulty. So that's how I will prove it. If I do the opposite, I will not be proving anything. Right? If you prove that it's easier, that the given problem is easier than a problem that is known to be NP-complete, that doesn't prove anything. Right? So I'm trying to prove hardness, not easiness. So this is one way of looking at this. Another way of looking at this is that this means that any instance of Ham cycle can be reduced to an instance of TSP. So this is what a reduction means, that given any instance of Ham cycle, you can reduce it to an instance of TSP, which means that if you have a solver for TSP, you can use it to solve Ham cycle. Now we'll see how. So you will assume that you have a solver for TSP. So this is TSP solver. Now, what's the input to the TSP solver?
Graph.
What kind of graph? Complete graph. Complete graph. And a target. Okay, great. And it gives you a yes, no. Now, the question is, I am given a TSP solver. I give it a complete graph and a target. And it tells me whether there is a simple cycle with this target with cost that is equal to the target or less. Now, how can I use this to solve the Ham cycle problem? How can I use it so that if I give it this, it's going to tell me yes. And if I give it this is not Hamiltonian because it doesn't have all the edges. It's going to tell me no. So the reduction is about using a solver for one problem to solve another problem. Now, in order to employ this solver, first of all, I have to put the graph in the form that this solver expects for its input. So I have to make these graphs complete somehow. But I want to make them complete in a way that will serve my purpose, which is solving this problem. So how do I make them complete? And how do I select the target such that the TSP solver solves Ham cycle for me? Any instance of Ham cycle.
So the edges that exist in that graph should have a weight of 1, and the other edges that are needed to make it a complete graph should be more than 1, and the target should be the number of vertices.
Okay, great. So basically the idea is to find a way to distinguish between the edges that already exist in the graph and the edges that I will have to add in order to make it complete. So I can assign higher weights to the edges that I add. So I can do 1 and 2, and because I know that the number of that in the cycle, there will be exactly V edges will be selected. Or I can just do 0. I can give these a weight of 0, and I can add other edges and give them weights of 1. Now, what should be the target that I pass to traveling salesman in this case? What target should I give it? 0. Yeah. So now, if I give the traveling salesman solver, if I input this graph, right, and give it a target of 0, I'm asking it to find a simple cycle that visits all vertices, but with cost equal to 0 or less. So it will find a cycle with cost 0 only if it uses the original vertices, the original edges. If it finds a cycle that uses the original edges, it's going to meet the target of 0. If it needs to use other edges, then this means that there is no simple cycle that uses the original vertices, the original edges. So with this one here, so here it's going to find a 0. Here it's not going to find a 0 because it will have to use one of the added edges. Okay, so this is our first example of an NP-completeness reduction. Okay, so in this case, given a graph G, construct a graph G prime, or construct a complete graph G prime with the following edge weights. So the weight of edge U and V equals 0 if UV belongs to E, where E is the set of edges in the original graph. So technically, we should write G as a graph equals V and E. So a graph is a pair that consists of a set of vertices and a set of edges. Mathematically, that's what a graph is: a set of vertices and a set of edges. So E is the set of edges for G. Set of edges for G. And 1 if UV does not belong to E. Now, G prime has a TSP tour of cost 0 if and only if G is Hamiltonian. Okay, so this is how we describe this transformation. Now, by the way, this has to be a polynomial time reduction. So is this reduction polynomial in time? So basically, our reduction is constructing a complete graph. So when it's complete graph, we're talking about V squared. That's certainly polynomial. And these are basically, it's a V squared transformation. Right? We construct this complete graph, and these are the edge weights. So you have E, and E is not going to exceed V squared. So we're talking about a V squared. It takes V squared time to do the transformation from the given instance of Ham cycle into an instance of TSP. Okay, so any questions on this reduction? Yeah.
So essentially, when we reduce Ham to TSP, we're proving that TSP is harder by giving a solution for the TSP that will solve every instance of the Ham problem.
Okay, like I said, you can view this as, so as proving that TSP is harder, or by saying that if I can solve TSP in polynomial time, I will be able to solve Ham cycle in polynomial time. But I'm given that Ham cycle does not currently have a polynomial time solution. Therefore, I cannot have a polynomial time solution for TSP solver. Okay, so you can think of this as proof by contradiction as well, right? So you are given that Ham cycle is known to be NP complete. So NP complete means it does not currently have a polynomial time solution. Nobody knows a polynomial time algorithm for solving it. So now by reducing Ham to TSP, you are saying that if a polynomial time solution to TSP exists, I can use it to solve Ham. And this will contradict what you are given. You are given that Ham does not have a polynomial time solution, right? So this is another way of looking at this. But the easiest way is to just think of the reduction as proving that the problem that you reduce to is harder or more general than the problem that you are reducing. So when you reduce Ham to TSP, you are basically showing that TSP is harder, is more general. Any instance of Ham can map to an instance of TSP. Yeah.
So even though we just proved that that Ham or TSP is harder than Ham, how does it prove that Ham is NP complete? Is that just
We are given.
Oh.
We are given that. So given that Ham is known to be NP complete.
Oh.
So we are assuming that we know that Ham is NP complete. We are using this to prove that TSP is NP-complete. This is just an exercise, right? So we're not trying to prove a new problem to be NP-complete. You know, both problems are known to be NP-complete. But we're giving this example to show how you can prove one problem to be NP-complete given the fact that another problem is known to be NP-complete. Okay, so in practice, you know, if you encounter one problem, you call it problem X, and you want to prove that X is NP-complete, you will look for a similar problem in the list of problems that are known to be NP-complete, and you will find a problem Y that looks similar or close to X, and then you reduce Y to X. And then you will prove that X is NP-complete. Okay? So now let's take another example. So to do another example, I have to define another problem. The problem that I will define is set partition. Given a set S of integers, determine if S can be partitioned into two subsets with equal sums. Now, what problem does this remind you of? Subset sum. Yeah, it's very similar, very close. That's why you know, when you do NP-completeness proofs, you try to find a problem that is similar or close. Okay. Now let's take an example. Example 2, 3, 4, 2, 3, 4, 7. Well, let's first take 2, 3, 4, 8, 1. So can you partition this into two subsets with equal sums? Yes. So the answer here is yes. I can partition it into 2, 3, 4, and 8, 1. So I managed to partition this into two subsets with equal sums. So this sums to 9 and this sums to 9. Okay? Another example is 2, 3, 4, 7. So in this case, can you partition it into two subsets with equal sums? No, you will not, because this is the largest number, so these will not give you 7. Yeah, 2 and 7 will give you 9. You will not find a way to partition this into two subsets. So the answer is no. Again, you know, this is another NP-complete problem. So if it doesn't have a polynomial time solution, so you know, in order to determine if there is if you can partition it into two subsets with equal sums, what will you have to do in brute force? So you should consider all subsets. So you look into all subsets and you see if the sum of the complement of that subset is equal. So you consider every subset, and for every subset you check if the sum of elements in that subset is equal to the sum of elements in the complement of that subset.
So we cannot take subsets which has only one element?
Subsets that have one element?
Yeah.
Yes.
Like, a set with only element 7 is a subset of this, right?
Okay.
So 4 and 3 and 7 will have.
But this is not a partition. A partition will have to use all elements. So a partition by definition has to use all elements, and each element can appear in only one partition, right? So you cannot skip elements. You have to use all of them. Okay? So this is set partition. Now, let's see if we can prove that this problem is, well, let's try to prove that if we know that this problem is NP-complete, we can prove that subset sum is NP-complete. So now, assuming that, or let's write it here, we're done with this. Now, assuming that, of course, both of them are known to be NP-complete, but we're doing an exercise. Okay, we're doing an exercise to show reductions. Assuming that set partition is known to be NP-complete, prove that subset sum is NP-complete. Now remember, don't forget the first condition. Okay, don't forget the first condition. So number one, you have to show that the problem that you are trying to prove is NP-complete, which is in this case subset sum. You have to show that it's verifiable in polynomial time. So subset sum is verifiable in polynomial time. And we have, fill in the blanks here. So we said how to verify subset sum in polynomial time. Verifying subset sum means that if someone gives you a subset, so the problem is you are given a set and a target. So if someone gives you a subset and says that I claim that this is a correct solution, you can easily verify that it's a correct solution by checking that the elements that they are giving you are in the set. So this can be done in polynomial time. And then summing these elements and see if the sum is equal to the target. Okay? Now, the more interesting step is verifying or reducing. Now, in which direction do we need the reduction? So in which direction should the reduction go? From subset sum to set partition, or from partition to subset sum? So we go from the known to the one to be proven, or from the one to be proven to the known?
One to be proven to.
Yeah. So no, you go from the known, right? It's this. So the one that we are trying to prove should be here. The one that is known should be here. So we're trying to prove that this is greater. So we're trying to prove subset sum. So subset sum should be here. And the known, the one that is assumed to be known, the set partition, should be on the left-hand side. Set partition. Again, this is the one to be proven. You have to prove that it's greater than or equal to the known one in terms of difficulty. Now I assume that I have a solver for which one? I assume that I have a solver for this. I assume that I have a solver for this, and that any instance of set partition, I can reduce it to an instance of subset sum. So assume that you have a solver for subset sum. Now this solver for subset sum, what does it take? It takes a set, and it takes a target, and it gives you yes, no. So this is subset sum solver. So now how can I employ it to solve the set partition? So the examples are 2, 3, 4, 2, 3, 4, 1, 8. This should give me yes. And if I give it 2, 3, 4, 7, it should tell me no. So how do I use a subset sum solver to solve this problem? So what set and what target should I give it?
We know that the target will be the total sum upon 2 of the set.
The total sum
By 2.
divided by 2. Exactly. So this is very obvious. You are trying to partition this. So your target is going to be the sum divided by 2. So you just give it here, what's the sum? 18. So you give it 9. Because the sum of these items is 18. So you give it the target equals sum divided by 2. And S is just the given set. So, well, let's use different, let's use just different symbols. So if, let's call it S prime. So this is the given set. So just use the same set. Okay, S equals given set, and that will, instead of trying to introduce notation, S equals the given set, and T equals the sum divided by 2, and that's it, right? So it's very easy to see how we can, I give you a solver that you give it any target you want, and it tells you if there is a sum of this target or not. So if you want to split this set into 2 equal parts, you just give it a target as half the sum. And then it will tell you if it can be split in half or not. Okay? Now what is trickier is to solve the problem in the other direction. Okay. So any questions on this first? Okay, now to solve the problem in the other direction, now assuming that subset sum, is known to be NP-complete, prove that set partition is NP-complete. Okay? So now you need to say that set partition is verifiable in polynomial time. So now who can describe how can we verify set partition? What does verifying set partition mean?
Both the sum of the elements in both the subsets are same.
Yeah, exactly. So a proposed solution to set partition is 2 subsets. Someone gives you 2 subsets. So you first check that the sum of elements in both subsets are equal, but you also have to check what?
Whether they belong to the actual set or
that all the elements belong to the elements of the original set, and you also need to verify that there is the intersection of the 2 subsets is phi, is empty. They do not intersect, right? And you also need to verify what?
their union is equal to the actual set.
Yeah, exactly. Yeah, exactly. So you need to verify that it's a valid partition, which means their union is equal to the original set, and their intersection is phi, the empty set, and you need to verify that the sums are equal. So, and you can do this in polynomial time, right? Everything that we have mentioned can be done in polynomial time. Now we need a reduction from subset sum to set partition. Subset sum to set partition. So now we assume that, so does this look harder or easier?
Easy.
Easier? So, okay, so how to do it? So tell us how to do it then. I don't think it's easier. For me, it's harder. Okay, it's harder because, you know, which of these two problems looks harder on the surface? You know, when you look at these two problems, which one looks more general? Yeah, subset sum looks more general. You know, it's clear. You know, clearly, set partition is clearly a special case of subset sum. So it was very easy to see how to use a subset sum solver to solve set partition, because set partition is clearly a special case of subset sum. A special case in which, you know, the target is the sum divided by 2. But now you are assuming that you have a solver for set partition. And the solver for set partition takes only S as input. So somehow you have to encode the target, because an instance of subset sum will have a set and a target. So somehow you have to encode the target here and employ this solver for set partition to solve subset sum. So for an example, you know, let's use this, and let's say our target is equals 12. So use this example. You have this set and your target is 12. So should the solver say yes or no?
Yes.
It should say yes, because you have 4 and 8. So it should say yes. How do you make it say yes? How do you make this say yes? It doesn't allow you, you know, it doesn't take the 12. You can only input a set, and it tells you if you can split it in half or not. That's what set partition does. You give it a set, and it tells you if you can split it or not. How can you use this to solve this problem, which has, you know, which takes two parameters, the set and the target? Yes. Yes.
We can add one more element to the set, which is the total of the set minus the target value.
Okay. Okay, good. So the target here is 12. And you want to add an additional item, which is the sum minus target.
Yeah.
Sum minus target. So what's the sum? Sum is 12 plus 5, so 17. 17 minus target, 17 minus 12 is
5.
17 minus 12 is 5. So you want to add a 5. So you add a 5. Okay. So will it be able to split it in half then? So you're close. So it's not quite. So you add an element. But how do you select the value of the element such that if this solver manages to split it in half, it will give you the target that you want. So if this manages to split it in half, it should give you the target that you want. So what should the half be?
2 into target minus the sum of the set.
Okay, yeah. So if the half, let the half be your target, because this is just a splitter. You know, it tells you if it's splittable in half or not. So now, if you want the 12 to be the sum of one of the partitions, let it or force it to have another 12. So to make it have another 12, then you add another element that is equal to sum 2 times sum minus target. Twice the sum minus the target. So twice the sum is, what's the sum? The sum is 12 plus 12 plus 5.
17.
Yeah, 17. Sorry, it's not. Yeah, it's not 2 sum minus target. So you want the whole thing. You want the whole thing to be equal to 2 times the target. So you want this, the whole sum, you want it to be 24, because you want this 12. So you want the whole sum to be 24. So it's 24
Sum minus target minus the rest of the elements in the set.
Okay, so it's 2 times the target, which is 24, minus, so what do you need to add?
Rest of the elements.
Yeah, the rest of the elements, which is minus 5. Or, in fact, the target, 12 minus, sorry,
2 into target minus sum.
okay, so what you want here, you want the total sum to be 24, and that 24 should include the 12 and the 2 and the 3. So it's 24 minus 12 plus 2 plus 3, and this is 17. Yeah, so this is going to be 17. So 24 minus 17, that's 8. Yeah. So it's, if you
It's 7.
7.
sorry, yeah, 24 minus 17 is 7. Sorry. Okay, so if you add a 7, then if you add a 7, then the 7 plus the 2 plus the 3 is going to give you a 12, and you have 4 and 8 equal to 12. Okay, so now 7 plus 2 plus 3 is 12, and 4 and 8 is 12. So if you give it this set, and if this solver manages to split it in half, each half will be the 12 that you are looking for, the target that you are looking for. Okay, so this is in fact 2 times the target minus the sum of elements. So it's 2 times target minus sum of elements minus sum. But in fact this will be the case if your target is greater than half the sum. If your target is not greater than half the sum, well, in fact, you can always assume without any loss of generality that your target is greater than half the sum. Why?
We know.
You can always assume that your target is greater than half the sum without losing generality.
Because both sets have equal sum of weights, that's why.
Yeah, well, because if your target is 12, solving the problem for target 12 is equivalent to solving the problem with target 5 in this case, because it's looking for a subset that sums to 12 is equivalent to the problem of looking for a subset of size 5. So for every target, you can also look for the complement of that. right? So if the target is not already greater than half, you look for the target. So if your original target was 5, I can do 12, because I know that the sum is 17. 17 minus 12 is 5. Okay, so in this case, let add an element an additional element, an element with value equal to 2 times target minus sum. Or construct S prime. You can say construct S prime. S prime equals S union A, where A union A, where A equals 2 times target minus sum. Then S prime can be partitioned if and only if S has a sum, a subset that sums to T. Okay. Okay, so now this is, this reduction was trickier, right, than the reduction. Now, it was trickier because on the surface, subset sum looks more general. But in fact, we have proven that they are both at the same level of difficulty. We were able to do the reduction in both directions. We were able to reduce subset sum to set partition and to reduce set partition to subset sum. So we managed to do the reduction in both directions, which means that they are both at the same level of difficulty. In fact, all NP-complete problems are at the same level of difficulty, but within a polynomial. So it's so the difference in the complexity of the algorithm that can solve one problem. The algorithm that can solve one problem can differ from the algorithm that can solve another NP-complete problem by polynomial only, not by exponential or factorial. Okay, any questions on this? Okay, so that was the second example, which actually included 2 examples. Let's now introduce more problems, and hopefully we have 15 minutes. So now we will introduce 2 problems. First problem is vertex cover. All of these problems are known to be NP-complete. But we will be doing exercises, assuming that one is known, prove that the other is NP-complete. So vertex cover is a problem that can be described as follows. If I give you a graph like this, A, B, C, D, and E, okay. Yeah. So if I give you a graph like this, now you are given a graph. You need to find a minimum number of vertices that covers all edges. So you need to select the minimum number of vertices such that every edge in the graph is covered. So here clearly, A, because it has many edges, so if we use A, we cover this edge, this edge, this edge, and this edge. So if we use A, we will cover 4 edges, but we will still have one more edge to cover. So we can cover it using C or B. Of course, this example makes it look easy. But in general, this is a hard problem. So, one possible application of this is that, suppose that these edges represent roads and the vertices represent intersections, for example. And you would like to put, a certain traffic sign such that all roads will have it. Or you want to post an ad, for example. You want to post some ad and you would like to have to cover all roads. So an intersection, when you put it at an intersection, you cover all the roads that intersect at that point. So if you put your ad at A here, you are covering 4 roads. So vertices that have more edges incident to them will cover more edges. So now what's the minimum number of ads that you need to post such that all roads are covered? Okay, so this is one possible application of this problem. So we can easily describe the problem given an undirected graph find the minimum minimum number of vertices that cover all edges. Okay, and in this example, we have an example. Now, is this an optimization problem or a decision problem?
It's an optimization.
Optimization.
It's an optimization problem. Now, so this is optimization. Now, what's the decision version? Vertex cover decision.
Give me a graph.
Whether it covers.
And the target what?
Target is a
minimum
vertex.
number.
Well, not minimum.
Number of selectable nodes.
So you're given a graph and a target what? What's the target here?
Edges.
No, 2 is the solution to this example.
Yeah.
Okay, so 2 is the solution to this example. What should the target be?
Set of vertices.
Minimum number of vertices.
Well, a number of vertices. T is a number of vertices. So vertex cover decision given an undirected graph and a target T, determine if all edges can be covered using T vertices or less. So to transform or recast an optimization problem into a decision problem, you look into the quantity that you are trying to minimize. What's the quantity that you are trying to minimize here? The number of vertices. So you set a target for the quantity that you are trying to minimize. The quantity that I'm trying to minimize here is the number of vertices. So I set a target. I see, okay, can I do it with T or less vertices? So this is the decision version of the vertex cover problem. Now, the other problem is the set cover problem. So the set cover problem given a set S and M subsets of S find the minimum number of subsets whose union gives S. So for example, 5, 6, 9, 3. This is the set. And the subsets are 5, 5, 9, 3, 6 and 9, 6 and 3. Okay. So we need to find a minimum number of subsets. So we're given a set and 4 subsets. We're given a set and 4 subsets, and we need to find the minimum number of subsets that cover the original set. So which subsets can we use in this example? So clearly this is going to cover 3 elements for us, right? So this will cover 3 elements, 5, 9, and 3. And we need another set that covers 6. So we can pick one of these 2. And that will cover 6. Now with these 2 subsets, we managed to cover the original set. So the answer here is the minimum number of subsets that cover the original set is 2. So now let's recast this as a decision problem. Set cover decision. Now what's the quantity that we are trying to minimize?
Number of sets, subsets.
Number of subsets. So this is the quantity that we are trying to minimize. So to convert this into a decision problem, what do we do? Set a target for this quantity that we're trying to minimize. So set cover decision given a set S and M subsets of S, determine if S can be covered using T or less of the given subsets. T or less of the given subsets. Okay?
And this is NP complete?
Yeah, both of them are NP complete. Now, the question is, knowing that, given that vertex cover is known to be NP complete, prove that set cover is NP complete. So the question is, given that vertex cover is known to be NP complete, known to be NP-complete, prove that set cover is NP-complete. Now the first step, we need to show that set cover is verifiable in polynomial time. So set cover belongs to NP, and this is usually easy. This verifiability part is usually very easy. So how do we verify that set cover is verifiable in polynomial time? What does it mean?
Just check if all the elements of subsets are.
So someone is going to give you two subsets. Not two subsets. A number of subsets, T subsets. Someone is going to give you T subsets. So first, you should verify that the given number of subsets is equal to the target. So if the target is 3, they should give you 3 or less. Then you just make sure that you take the union, and if the union gives you the original set, you are done. That verifies it. So verifiability is usually very easy. Now the tricky part is so you just write down what we have just said. Now we need a reduction, need to reduce set cover to vertex cover, or vertex cover to set cover? Yeah, vertex cover to set cover. So now I assume that I have a solver for set cover. So it takes S, and you can give it subsets. Let's call them T1, not T. Maybe, okay. Yes, R1, R2 through Rm. So now, how can you reduce vertex cover to set cover? So I give you a solver for set cover, and you have a vertex cover instance. How can you transform any vertex cover instance into a set cover instance? So think about what covers what. What is being covered and by what? So in vertex cover, a vertex or a set of vertices covers
all the
edges. So in set cover, set of subsets covers what?
original set. All the elements of the original set.
Yeah, covers elements. So we're trying to find a mapping between the two problems. So in this case, vertices cover edges, and here subsets cover elements. Well, so how do we do this mapping?
We can pass the vertices as the set, and for every vertex.
Well, the vertices as the set, so what is to be covered is the set of elements. So we're trying to cover the elements.
We pass the edges as the.
We pass the edges. Yeah, so it looks like we're running out of time anyway. So we will, maybe we should give you this to think about for next time. Try to get this figured out without Googling it. Okay, so try to practice. Instead, you can Google it and then you will find a solution somewhere on the web. But try to use it as an example for practice, because we will do it next time. We're almost done with the material.